So let's actually do some analysis of the values. And then I want to come back to Jolene's interpretation of the 1, 2, and 3 standard deviations. Pretty slick, actually. I'd like to remember that. So we don't want to use that formula we just took a look at on the PowerPoint. That's a no-no. So how do we get it else in any other way? Well, it's actually the same command you already used, var stats. So if you quit out of the graph screen momentarily and go stat calc, this is the same place we went last week. And you're still going to grab var stats. Press enter. Now what you don't want to do right now is just press enter. Now I'm going to show you why. I can. I just did. Even though I told you not to. And it's going to give you numbers. But those numbers are incorrect. Can you tell why they're incorrect? Boom! Yeah. Monica and Pat have noticed it's only looking at L1. And you can tell that right here. You know that n is bigger than 7. There are more than 7 people in the top group of data. But if you just hit var stats enter, it's going to think you're only talking about L1. L1 is your data, and therefore there's the data, which means you got answers that don't make any sense. Fair? Yeah. So what we have to do is go stat calc var stats.
You're going to do L1 and
L1 comma L2. This is how you override the default, and you tell it, I want my data in L1, comma is right above 7, just so you all know, right above 7. Comma L2. We'll figure out how to do this on graph. They would probably do it. Got to do it. If not, we'll find out. Let's talk about that. I don't want you to spend.
L1.
Second one. Same way you got L1 and L2 for the graphs.
L2.
Make sure you put a comma between them, which is kind of hard to see with this damn string in there.
I didn't.
There we go. Sorry.
We might try to do a letter to add the alphabet.
Press the alpha button. Press that green button. Yep. That turns the alpha mode off. It's all good. I'll say it again. We're all learning. We're all learning. Cool so far? Press enter. Notice the difference in the results from the last erroneous screen. The last erroneous screen said the average age was 49.5. Well, that is if you had 7 data points, 1 of each, and 49.5 is in the middle. But that's not the case when you actually look at the frequencies as well. Now your average age for the top finishers is about 34 years ago. So we'll do the top finishers. Their average age is about 34 years with a standard deviation of about 9. With a standard deviation of about 9. So we have an idea of spread. Now the thing is, we don't... I told you 2 things about the relative size of S. When S is big, data is spread out. When S is small, it's tightly clustered. The problem is, what's 9?
How many points are...
Good. Thank you, Libby. Yes, it's the average distance a data point is from average. But is this data spread or is it clustered?
It's hard to tell.
There's no comparator, correct? Why don't we compare it to the other data set and see how the data is clustered? Now, I'm going to ask you a question before we do that. I'm going to press graph again.
How did you know that was just the top?
Oh, how was that one? Let's go back to that question real quick. So, Veronica's question is, how do we know it's this one and not this one, both of which round to 9?
No, that's not what I meant.
That's not
How do you know that that's the top? The data
oh, because I put the top finishers in L2.
Okay.
That's the frequencies I put. I put the bottom finishers in L3.
And you asked for L2 here?
I did. Oh, you can't see it right now. But when we typed it, it was var stats L1, L2.
Okay.
We're about to do var
Gotcha.
stats L1,
Okay.
L3 and compare it. Vivica, go.
I just can't get
You say that again?
I just can't get my tour.
Oh, we'll come back and take a look. I promise. I want to ask the question that I thought Veronica was asking. So we're definitely looking at this. We like that number because that's the average. You can ignore that. You can ignore that for the most part. This is kind of nice sometimes. It tells you did it right because there should be about 80 data points there. Then you got these 2 guys right here. Pat, this is an answer to a question you asked 30 minutes ago.
Population.
That's your population standard deviation, which you can go ahead and ignore for right now. It doesn't make any sense because this is a sample. That's what this guy is. So that's why the only 2 real numbers of center and spread on this first page are X bar and little s. You can ignore that little sigma at the bottom. I'll come back to why he's even there. Linda, go ahead.
Can we get another cheat sheet like you did for 105 for this?
It exists on the web page. If you go to the enrichment page, there's a document called a reference for statistics on the TI 83 and 84.
And it tells you step by step.
Step by step how to do all this stuff. Yep.
Nice.
Yep. Yeah, it's all there waiting for you guys. Yep. Cool. Excellent. Excellent. And every once in a while, I'll record videos and put them on YouTube. But honestly, the ones that are out there already are infinitely better than the ones I'm making as far as the TI goes. I haven't figured out how to record them well with the TI. So if you ever need like how to calculate a standard deviation on a TI, just Google it and put it in YouTube and look for it. I'm not trying to pawn off the work off of me to somebody else, but they've already done it and it's already good, so why not just use it? I can record the other stuff that they haven't done yet. Yeah, Pat?
I found a app too, like there's a bunch of free apps on like standard deviation.
Mm-hmm.
I know
Smartphones, the App Store.
So I cheated on one of those quizzes.
What? We are redefining the word cheating in this class. I encourage cheating. I encourage it. I want you to use your resources. I don't want to deny you the resources. Use the resources. It's not cheating. Don't feel bad about going to the App Store and downloading a stat cheat sheet. I encourage that kind of crap. Yeah, I want you to do that. I want you to. A cheat sheet is not going to help you understand what standard deviation is. It's going to help you get that number.
Yes. It's
not going to tell you how to interpret it. That's what we do in class. Cool?
Yeah.
So speaking of which, let me erase all this. My next question was, who's going to have a larger standard deviation, the top or bottom finishers?
Just by looking at the data.
By looking at the graph of the data right here, who do you think is going to have a larger standard deviation?
Bottom.
Bottom. And what's the giveaway? Do you think? You've got a longer. It's got more of a spread. I mean, you've got more data. Your average is at 34 for the top finishers. What do you think the average is going to be for the bottom finishers? Ish.
435.
A little bit to the right? Yeah? This was my first question to you guys before. Are the averages different? You know what my gut feeling was? Not really. I mean, yeah, they're going to be different. Mathematically, they're going to be different. But statistically, I think I'm guessing, based on that data, they're going to be within 5 years of each other. I haven't actually run it yet, so I don't know. I'm guessing. Some of you have already done it. You can prove me right or wrong. David, go!
So to get the top or the bottom finisher, you're looking above the line or below the line?
Above or below? Oh, the histogram is the top finishers. The line is the bottom finishers.
Okay.
Does that make sense?
Yeah.
So the thing about the TI that sucks is you can't put two histograms up. So you can imagine a differently colored histogram right here, if you do it this way. But then that gets in the way too. That's why I did it with the line graph instead.
Okay.
But let's figure it out. Let's figure out where the bottom finishers are. See how good my predictions were. This guy might throw my average off a little bit. We'll see. So now the question is, again, without using some cumbersome formula, how can we pull these numbers off of the graph? Well, exactly the same way you just did, but just change the L2 to L3. Exactly. And what's totally slick, and you guys in 105 know this already, you can press second enter, and that calls up the last command you entered. Which means you don't have to go back in and go through stat calc second one comma. You can just pull up the last command and change the L2 to an L3. That's a slick command. Second enter. Second enter is a really, really nice command. We used it a lot in 105 when we were doing computation after computation after computation. And it saves you the time of having to go back and find submenus again. You may have forgotten it from 105, and that's okay too. So we do it again. You also can just go back and go through stat menu again if you want to. I'm sorry, I didn't upset anybody. If I start hearing swearing, I get nervous. Here we go! Here we go! See, I was wrong about the average. The average is much higher than the lower ones. About 43 and a half, I'm gonna call that 44, we're off by a decade. And the standard deviation, just like you guys predicted, is larger. Because the data is more spread out. So those goofy little tail units at the far right are pulling the average further than I thought they were. This is why you have statistics, because your gut sometimes steers you the wrong way. Ah, they're the same. No, they're not the same, Sean. Look, they're a decade different. Okay. This is why you have statistics. Pat.
And then that 75 is the total number of data points.
Yes, in L3.
Right.
Yeah, so there were 75 data points in the bottom. There were 81 in the top. I don't know why they're different. I just did a random sample, pulled it from the top and the bottom. I have no idea why I pulled that number of them. There you go. Now, let me ask a question. What can we now infer? Let's go back to the top finishers. Now that we know that X bar is 34 and S is 9, and more importantly, and I'm going to turn off the bottom finishers and just look at the top ones. What can we now infer more deeply about the percentage of finishers in the top. Now that we know the standard deviation and the average, and we also know that the data is roughly bell-shaped. Well, younger than the bottoms?
Yeah.
Good, that's 100% correct, but forget the bottoms for a second, just look at the tops. For example, the average is 34, correct? If I apply the 9 to 34, I'll go from 23 up to 43, yeah? 23 to 43? What do I know about that range of ages from 23 years old to 43 years old? How many are in there? About 2/3, huh? Remember what Jolene started the class with today? She's like the empirical rule. There's about 2/3 of the data. So what that means is you can now, assuming that's a random sample of those top finishers, 2/3 of the top finishers are going to be within 23 and 43 years old. In other words, 9 years away from 34. I did that math wrong, didn't I?
Yeah.
It's 25 to 43. 25 to 43. So if you add and subtract this from this, that's one standard deviation, and roughly 2/3 of the data is going to be within that. You can't get that unless the data is bell-shaped. That's the only time you can do that, is when the data is bell-shaped.
Yeah.
Plus or minus 9, plus or minus 9. Good so far? Fair? What if I plus or minus, what if I add and subtract, sorry about that YouTube world. What if I add and subtract 18 years from average? What if I go 18 down, which would be, what would that be? 16, and 18 up would be 52? Between 16 and 52 years of age?
95%.
That's about 95%, yes. That's 19 out of 20 finishers are between 16 and 52 years of age. And the reason I bring this up is some people say, hey, my son just ran the Portland Marathon. He did really, really well. How old is he? He's 13. Then you go, holy crap. Because 95% of those in the top are between 16 and 52. Your son, if he ran it, or daughter, if she ran it, if she's 13 or he's 13 years old, you go, holy crap, that's really, really rare, isn't it? To finish in the top and be that young, because you're outside of that realm of 2 standard deviations. It gives you kind of a quantification of how unusual something is. More on that to come next week, I promise. Assuming we don't have skating rink conditions on the roads again. But more on the idea of outliers, which this is a good way of measuring those kinds of things. And we could go out 3 standard deviations, but it doesn't make a whole lot of sense to do that right now. It gets a little ridiculous because when data is not perfectly bell-shaped and or when it can't go off infinitely, like we could go out 5 standard deviations technically. You know, because bell curves go forever, but the problem if you go 5 nines is 45 down from 34. What kind of numbers are you into? Negative ages, which don't make any sense. Like my sperm ran the marathon, doesn't make any sense. So eventually there's a practical limit to how far out you can go with this kind of analysis. But usually 1 and 2 standard deviations or 2/3, all the 2/3. If you go out 6 years, 2/3 of a standard deviation, so you go down to 28, I guess, and up to 40. Half of them are going to be between 28 and 40. So it gives you that kind of quantification of how many are close to average and how close to average. Is that fair? I like the bell shape. I like that bell rule. It's a nice one. Of course, you can only use it if you have arguable bell shapes. Which brings us to the next topic. So, have you ever heard of, there's a paper printed in 1991, which I know is dating me and the paper, but there was a paper